Hello. You should see the desktop. You should hear me. Does everything seem okay now? Everything working? Do you hear me? Oh, okay. Yes. All right. Okay, great. Okay. So here's what I want to do today. I want try to continue explaining the subtlety between language 7 and 8. The goal is to try to understand why language 8 is really how it's different than language 7. So I came up with one way of doing it. Like, okay, let me download language 7 and 8 because I want to compare them. Okay. And whoops. Okay. Okay. Now we did some. Oh, we did some examples last week, and I hear I put the the C versions of these examples. Um, the idea here was that we were assigning functions to values. Okay. Now let's like back up a minute. Language 7 is described as a language with global first-class functions, whereas language 8 is described as a language with first-class nested anonymous functions. Okay, so language 7 is global first-class functions, and this one is nested first-class functions. Okay, actually, I should reverse the order there to make it. The differences between nested first-class functions and global first-class functions. Okay, so first, what do we mean by first class? So, uh, if we, it'll help if we say, what does first class mean? We know what global means, but what does first class mean? Then over here, first class will have the same meaning. And then the question, what do we mean by nested? And also, what do we mean by anonymous? Okay, so what does first class mean? It's what we did the other day. You can assign a function to a value. Uh, you can store function. You can make a function a parameter to another function, a return value from a function, or you could store it in a variable. Okay, so first class means that you can treat functions just like you treat other values, like integers and booleans. You can store them in variables, pass them as parameters to functions, and return them as values from functions. Okay, so the example we did in class were was I was using the example of a real famous example, callback functions. A callback function is when, like, you have a mouse handler function. So there's a variable that's going to hold what the mouse handler function is. There's a variable that's going to hold what the key handler is. Okay, then here's the function that is there's the function that oh, let's see. Oh, okay. Th- This is a function that takes as input a function and stores that input function in that variable. So it's called registering the mouse function. So that's saying, that's the way you say, here's what function I want to be the mouse handler. So this is an example of of using a function as a parameter to a function. So I've got a function that takes in a function as a parameter, and it stores that value in that variable. So it's taking a function as a parameter and storing it in a variable. So it's using a first class function in two ways. Then register key is a function that takes in a function and it stores that function in key handler. Okay. Now I define a squaring function and a cubic function, and I make the squaring function the mouse handler, and I make the cubing function the key handler. Okay. All right. So yeah, I mean, I'm not really doing event-driven programming here, but I'm showing you that the key idea in event-driven programming is the idea that you can store functions and variables. You can say register this function as the as the mouse handler. Register this function as the key handler. Then those functions are stored in some global variable somewhere. Then when a mouse event or a key event happens, you call the key handler. Notice you're not calling square, calling key handler. But key handler is set to, well, key handler is set to the cubing function. And here we're not calling square, we're calling mouse handler. Okay, mouse handler is a variable whose value is a function. Okay, and if you let's see, now let's go ahead and run that so you can see it happen in. Yeah. But this is demoing first class functions, and you can do this in C. First class functions. If you go back far enough in history of programming, there were languages that didn't even have first class functions. You couldn't set a variable equal to the value of a function. Okay, but since about the 70s, all functions could do it. Though in some languages, even like C, if you look at the C versions of these functions, they're kind of hard to read. Okay, this is what it looks like for a function to take a function as parameters. It can be very hard to read these things. Okay, so C lets you do this kind of thing, but it doesn't make it very easy. Now let me download that just and this one, and I can run them in language 7. Okay. Okay, so if I pull these into this folder, okay, I have to build the interpreter. So build all the classes. Oh no, I'm sorry. The interpreter is already built. I'm sorry, it is already there. There's the jar. Okay, clean it. Yeah, the jar file is right there. So open a command window. Okay, run the interpreter with that is the example. So run that program through the interpreter. Okay, and if you step through it, so we can watch it we can watch what's happening. Here's what the code looks like. There's a register. There's the two global variables that are going to remember what's the mouse handler and the key handler. This function takes in a function and stores it in mouse handler. This function takes in a function and stores it in key handler. Okay, then here's a couple functions. Then register squaring as the mouse handler. Register cubing as the key handler. Okay, so we're just storing a function we're passing a function to one function, which then stores that function in a variable. So that's just using this function as a first class value a couple times. Using it as a first class value is making it the parameter to that function, and then using it as a first class value by storing it in that variable. Okay, then here call the key handler. Yeah, well, by calling the key handler, I'm really calling what's stored in this variable, and what's stored in that variable is what I registered here. Okay, so then you go through and watch it. Okay, there's the mouse handler variable, which has just got a dummy value in it to begin with. There's the key handler variable, which just has a dummy value in it to begin with. There's the definition of the register mouse function. There's the definition of the register key function. Okay. Okay, here's the definition of the squaring function, the definition of the cubing function. Okay, now here was calling the this line, this here was calling there, calling register mouse and passing it the squaring function as a parameter. Okay, so that's called, and see f, the parameter is the squaring function. So that's calling register mouse and giving it the squaring function. And when it's done, you'll see that the mouse handler now points at the squaring function. See, now the mouse handler stores a function value. Okay. Notice that the key handler still holds it's actually the key handler is holding an integer value. That 0 is just a temporary value. But now the mouse handler holds a lambda, and the lambda is the squaring function. Okay. So now this next call is going to store, the next call is the call to register key. Okay. And it's gonna, no, let's see, that's this one here. Here's the call to register key. It takes the cubing function and it's going to store it in the key handler. Okay, so when it's done, we see that the key handler now is got that in it. Okay, okay. Now we're applying the key. Now we call the key handler function with the parameter 5. Let's see. Lost track of which one's which. I need more labels in these. I forget, this should have the name of the function that's being called. I think I thought I had that in there. It would be a lot easier to read to know that which function activation record this is. That makes it easier to read. And I thought I had it so that these things gave you the name of the function being called. Okay, so this one should be, this is registering the, that's calling register mouse. Okay, and then the mouse value is registered. This one should be, why is it again here? I don't know why this isn't repeated. I've lost track of why this one repeats here. Yeah, I've lost track of, you call this should be calling apply register mouse with the squaring function as a parameter. Okay, but I'm not sure what this one is offhand. You see, it's got the squaring function as a parameter again. Then it does, now here's calling register keyboard with the cubing function as parameter. Okay, and now when it's done, see the cubing function's been set as a parameter, but then it calls it again. I don't understand. I don't remember what these duplicates are. Like this one, it seems like it's being called again. Okay, now, so it seems, I've lost track of why those seem to be called twice. Okay, then you apply the key handler with parameter 5. Okay, that's this one. See, there's the 5 being called the key handler. Okay, now key handler is the cubing function. Okay, so 5 should be put into the cubing function. Okay, and then R1 gets back 125. See, this is the result. You cubed 5 to 125. So this was calling, now it says call key handler, but key handler actually is the cubing function. Okay, and then the last one is calling mouse handler with 5, but mouse handler is the squaring function. So we're calling the squaring function with value 5, and we get back 25. Okay, so yeah, except I'm not sure what those duplicates were. I have to go back and figure out why this line seems to be in there twice in the output. Offhand, I don't remember why that should appear twice. That's here, and then why it appears again here. Why does it appear twice? The same with the other one. Why? Offhand, I just don't remember why it was seen to show up 2 times. It might be something in the, it might just be that it's not being called 2 times. It might just have to do with the way the debugging output. Maybe the debugging output's got a repetition. Oh, I bet that's what it is. I bet there's some kind of repetition probably in the way the debugging output is printed out. So for some reason, the same thing's being printed out 2 times. It might even be like a little bug. Maybe there's some weird, something that's making this output be logged 2 times to the output, to debugging output. Okay, right. So we watch this. Now here we're seeing first class function. The idea that you can take functions, make them parameters to one method, store them in a variable. And a very famous example of using this is in GUI programming, where you use callback functions. Mouse handlers, event handler functions are literally this. These global variables belong to the GUI system. You call functions like this, register mouse, register key. It stores the function that's the keyboard handler or the mouse handler in these global variables. Then when an event happens and you call the key handler, it's going to call whatever function you stored in that variable. Okay. So it's using the idea that you can store functions in variables. And that goes back to the 70s and 80s with the invention of GUIs, this idea of callback functions. And that's when languages started needing first class. That's when languages started needing the idea of a first class function. People wanted to store functions in variables so they could call them later on. Okay? So, you would say, you would define the keyboard handler function. You tell the GUI system, here's what I want you to use for keyboard handling. And then when a keyboard event came in, the GUI system would call your keyboard handler. The GUI system would call the thing that you want to be the keyboard handler. Same when a mouse click came in, the GUI system would call whatever you told it is the mouse handler. So when people invented GUI systems, they realized the need for first-class functions. And so languages like C were designed to have first-class functions. Before that, people didn't pass functions around to other functions. You would just define a bunch of functions in a program and call them, but you weren't passing functions around like they were data. The key here is that the function is like a piece of data. The data I want to store up here is what function to call when a mouse event happens. And then I've got a piece of data down here that says, here's what function to call when a key event comes in. Okay, so register mouse and register key, calling register mouse says, here's the data I want you to use, which is a function when a mouse event comes in. Here's the data, here's the function I want you to use when a key event comes in. Okay, so first class functions are a real important idea. Again, we see this is just a little demo of them. Language 7 does them fine. Okay, now language 8 goes a little bit further. It has nested first class functions. What that means is you could put functions inside of functions. Or it doesn't just mean functions, it means functions can be inside of things. Okay. See, if you go back here, function, as I mentioned a few times before, is not in the list of expressions. Function only exists at the top level. See? So in a program, you could start the program off with a bunch of function definitions, and then you have the body of the program. The body of the program is an expression, and expressions cannot define new functions. Okay, that's the way the C language works. A C program, if you think about what a C program is, a C program would be some function, some other function, some other function, some other function, and then finally a main method. Okay, then the main method calls all these other functions that you've defined. Okay, but you can't define a new function in the main method. You can't say, you can't have some function f2 in here. You can't have a local function in there. Similarly, when you define function f, you can't put a function inside of f. You can't have f with a function. You can't have nested functions. This would be what we would call nested. Okay, this is a nested function because it's nested inside of main. So this is also a nested function. Okay, see, C doesn't allow that. Yeah, so okay, and Java doesn't allow it. A lot of nested functions are really it's these nested functions that start making us need language 8. Okay, now so nested just means that the functions can appear inside of some sort of group. They're not just at the top level. Oh, so this would refer to as a top level function. That's how we think of these. These are top level functions. They're not nested inside of anything. They're top level global functions. And main is a top level function. Okay. So top level functions, that's what language 7 is, and that's what C is. The only functions are top level functions. Okay. Now top level functions can call each other. So G can call F. G can make a call to F. H can make a call to G. Okay. Okay. So you can call top level functions. Functions can call functions, of course, but functions can't, you can't create new functions inside of functions. Okay. Okay. So that's what we mean by nested functions. Okay. First class functions are functions that can be passed around or stored in data structures. Nested functions are functions that can be embedded inside of other functions. Okay. Now, nested functions are much harder to implement than first class functions. Okay. And there's also weird interactions between nested functions and first class functions. Nested functions can be made easy if you don't let them be first class functions. Okay, so what's interesting is that there's nothing really particularly deep about nested functions as long as you don't make them also first class functions. Because what can go really wrong, what goes really wrong is when I do something like return G10. That causes all kinds of grief. Returning the nested function, we'll see, really makes a big problem. Oh, here's another example. Suppose I put a global variable up here. Try to think of a good name for it. I've already used FGH. I'll call it callback. Okay, so I have a variable here, callback. A real problem is if I do okay, here, this is a problem. Returning a nested function. And here's another problem. I'm not returning it. I'm setting this global variable to be the local variable. So um, you might just say escaping the nested function. The nested function kind of escapes from here out to this global variable. Okay. Now, the reason why this is going to cause a bunch of trouble is a local variable only exists while the function is running. So if down here, if you call h, okay, so you call h, while h is running, g exists. But on your hand, it sets g up here. It makes callback equal to g, but then when the function returns, what the heck is callback now? Well, we're going to make this more precise in a minute, but you can kind of get a sense of what's wrong here. I call h starts up. G is a, oh, I'm sorry. Oh no, I'm sorry. I wanted this to be one of the, make this a nested function here. Oh. Give h a nested function. Okay, so escaping the nested function. Okay, right. So you call h creates this local variable, which is a function, but these local things only exist while this function is running. So this function exists. I assign it to callback. This function returns. Now I come back here, and now I call callback. But now the thing that callback is pointing at probably is gone. That's the problem. The thing that callback was pointing at doesn't really exist so much because it was a local variable. So there's all kinds of funny issues about when a function, when a nested function escapes from what it's nesting in, then what does it mean at that point? Same thing's true over here. Like, okay, now f, it would look like this. Okay. With f, I would get a problem this way. I would say something like f 00 equals f. So call f. Well, when you call f, it creates this local function and it returns the local function. So now f00 is this guy, except that guy doesn't exist anymore. Because see, you called f, it created the local stuff. It took the address of that local stuff and returned it. So now this is the address of that local stuff, but then the local stuff was deleted because the function returned. So now if you try to call f of 00, what happens? Okay. So here you're trying to call the escaped function, but there's a question of what is it you're calling. And here you're trying to call the returned function, but there's a question of what you're calling. Okay. So when you have nested functions and you treat them as first class by returning them or assigning them to variables, then you have a problem. If you don't, if your nested functions are not first class, there's really no big deal going on. What that means is that you can only call them locally. So you could call G20 in here. Okay. So you could define G20 in here and you could call it in here. Okay. And that would be okay. There's no problem with this. The problem is when you treat your nested functions as first class functions. Okay. By, for example, escaping the nested function or returning the nested function. Okay. So what so let's look at a specific example of that. We're going to play with language 7 and we're going to try to make language 7 a little bit more clever. Okay, we're going to see if we can make language 7 a little bit more clever than what it started out as. Okay, so here's what I mean. So the issue is going to be, we want to get to this idea of what happens if you combine nested functions with first-class functions. What can go wrong when you try to combine them? Language 8 combines them, but it turns out to be tricky to combine them. To correctly combine nested function with first-class functions, you have to be very careful. Okay, so now what I did to try to make this, let me clean this up, is I defined a language I call 7E, E for error. Okay, language 7 or experiment. You can think E for error or E for experiment. We're going to play around with language 7 and make a couple changes to it. Okay, so in language 7E, I took fun and moved it into expressions. Okay, so I took fun and moved it into expression. That allows nested functions. Okay, so the first thing to do is I'm going to allow nested functions, because now you can define a fun inside of a begin, or you could define a fun inside of another fun. Okay, so now you can put funs. Now, no, I'm not putting lambdas down in here. I'm only putting fun down in here. That means I have nested functions, but not anonymous functions. What that means is I have nested functions, but not anonymous functions. Okay, so I could, for example, put a fun, I could open a begin and put a fun inside of the begin, or I could put a fun inside of another function. Okay, because now the fun keyword can be, you know, like here, you look at begin. Begin has a sequence of expressions. So what can be inside the begin? Well, fun is now an expression. So fun can be inside of a begin. So there, a little example of that was right here. See, begin, there's a fun inside the begin. Okay, I can make that easier to read by indenting it. So there's the fun inside of begin. Then I call it, and there's the end of the begin. So I have a begin block. Okay, the fun is defined locally, and then it's okay. Now, if we try this in language 7, okay, let's go back to language 7. And let's see what happens if we try that little piece of code in language 7. So here's this example 1. It's actually meant for language 7E. Let's try it in language 7. So open a command window here, call the language 7 interpreter, and give it, what does they call it? Example 1, language 7E. Okay. Okay. And I got invalid expression. Now, see, I tried to format it right. See, this is not allowed inside of a begin. So inside of a begin, a fun is an illegal, invalid expression. So it just didn't work. In the grammar for language 7, you can't have a function definition inside of a block. Okay, there's no nested functions. So the language 7 interpreter gave you, when it hit the fun definition, it, if we, the language 7 interpreter gave an error as soon as it got right there. You know, that's an invalid expression to be inside of a begin block. Okay, so it didn't work in language 7. Okay, so now let's make it work in language 7E. So go to language 7, go to language 7E. Now, what do we have to do to make that work? Okay, so let's think about the interpreter. We've moved fun into expression. Okay, so that means that, oh, if I, okay, go to the evaluator. Okay, fun is in expression. So that means in the table, here's the evaluate expression. it needs a fun term right at the beginning. Okay, so it needs to say evaluate fun. So it will evaluate funds. Okay. Now in language 7, you didn't have an evaluate fund. We had a handle fund because funds didn't return a result. Funds weren't expressions. They were just things that happened at the beginning of a program. They only put things in the global environment. So now here's what was handle fun. Now it's evaluate fun. And it used to, let me show you, compare what it was and what it is now. Okay. So in language 7, evaluate. Here was what it used to look like. So what we're doing is we're changing here's the old value, here's the old one, here's the new one. The old one was handle fun, which returned void because it didn't do any, it all it did was put the name of the function in the global environment. Now it's supposed to return a value. Okay, what it's going to return is the lambda expression. Now the code is exactly the same all the way up until the very end. What's new, if you look at the old one, all this is exactly the same. After it put the lambda expression in the environment, it just returned. Now, after it puts the lambda expression in the environment, it's going to return the lambda expression. That's all. So, that was supposed to be a step 7. So step 7's got one extra step. Now it returns the lambda expression. Okay. So from the point of view of the language, a fun puts the function it's defining in the global environment, still does that, and it returns a pointer to the function it created. Okay. But it lets you nest functions. Okay. Okay. So now we can allow nested functions. Okay, that's the only change so far in the language. We change handle fun to evaluate fun, and now evaluate fun, because it's an expression, fun can be anywhere. Okay, so now this little test program will work. Okay. Okay, this is the little test program. Oh, let me copy it from here. Here's the little test program. Whoop. Okay. Now I already compiled language 7. So open a command window here. Okay. So what I want to do, I want to run the language 7e interpreter on example 1. Okay. And it works fine. What it does, it creates a local variable, it creates a local function and then calls it. Okay. So in the global environment, it created, notice the global environment created a local environment for the begin block, and then the local environment stored F. So F is stored in the local environment, not the global environment, like it would have been in language 7. Okay. And then I call F. So here's the call to F. Okay. There's the activation record for F, and it's got 5 as the input parameter for X. Okay. And it returns 25 because it's just a squaring function. Okay. It worked fine. Okay. Now let's see where things can go wrong. See, right now, we're allowing nested functions, but we're also still allowing them to be first-class values, because now essentially, if we think about it, language 7e has got nested first-class functions. So language 7e is nested first-class functions. Okay, but we're going to see that that's going to be a problem. This isn't going to work very well. So we're going to play around and see what we can get out of this. See, it seems like it's working so far, but I've only used the nested aspect. I haven't used the first class aspect of the function yet. Okay, so let's look at another example. I'm going to start blurring. I'm going to start combining these. Well, here's the next example. I create a global variable. I create a begin block. There's the function f in the begin. Oh, this begin block's the same. It's almost the same as it was before. But here, what I do is I create the begin block, define the function, then use the function as a first class value and set the global variable to be that local function. Then I call the function using its global variable. So yeah, you could think of G as being the callback function. Okay, so here's a global variable that can store a function. Here's the local function, then I store f in the global variable, and then I call it after I've stored it. Okay, let's see if this works. So now I've got a nested function, and I'm using it as a first class value because I'm storing it in a variable. Okay, so does this work? Okay, so this is example 2. Okay, and it works. We can trace through it. It works fine. We haven't pushed hard enough yet to cause a problem. Okay, so here is the global variable. Here's the block with a local function. The local function is allowed to escape out of that block, and then I call the local function. Okay, okay, and it works. Okay, but what, yeah, and you can here. So here's the global variable with the dummy value in it, just the value 0. Okay, here's creating the begin block. The begin block gets f put in it. Okay, then here's the where G becomes a value pointing at that local function. So see now here in the global environment, G's value is that lambda. So G's pointing at it looks like it's actually pointing at that lambda, but the way the visualizer looks, it looks like it's copying it. This is actually not a copy of that lambda. It's actually really pointing at that lambda. But there's no way to show that in this kind of output. But this is a reference to that lambda. So this and this both reference the same lambda. That lambda is just a branch in the abstract syntax tree. If I go back over here, I can look at the abstract syntax tree. That lambda is this abstract syntax tree here. So G points to that abstract syntax tree, and so does F. So F and G both point at that branch, that abstract syntax tree branch. Okay. Then I call G. Okay, so that's the call to G with the parameter 7. Okay, and it calls G as the squaring function. So G is this lambda expression. So now we're at when we apply G to 7, G ends up pointing at that lambda expression. So that's the lambda expression we're evaluating. We're evaluating that lambda expression with input 7. So X is bound to 7. G is that lambda expression, and we get the right result. Okay, nothing goes wrong. Okay, so far so good. All right, now let's push a little bit harder. Okay, let's do something a little bit trickier. Okay, so I want this third example. Now, in the history of programming languages, this is what people were doing back in the 70s and 80s. They were playing with these examples, and they were thinking, what can I do? What's going to go wrong? What does my language allow? So we're kind of like duplicating the thought processes they went through of trying to understand what their languages did and didn't do. Okay, example 3 does something a little bit trickier. Okay, here's the example. Here's example 2, and here's example 3. Actually, let's see. Now let's go back to example 1. We'll see how they kind of grow. Example 1, declared a function locally and called it. Example 2, declares a function locally, stores it in a global variable, then calls it. Okay, so it just delays the calling of the function a little bit, creates the function locally, gives and then sets and passes it to this global variable, then calls it using the name in the global variable. Okay, now here we do something a little bit weirder. We're in a begin block. So create a local variable x and a local variable y. Now change the function f to reference the local variables. So f takes in a z, and what f does is it adds x, y, and z. Okay, now in the other examples, f had a parameter and didn't make any non-local reference. Notice that the function did not reference any variables outside of itself. Okay, so the function's self-contained. In the words we used before, this is a closed expression. See, the expression only refers to variables defined in the expression. Okay, now that's kind of important here. Okay, over here now, f uses local variables. This is an open expression. There are references in there that are not part of this expression. Okay, it's referring to that and that variable there. So y comes from there, and x refers to there. Okay, then I'm going to call f. Okay, this isn't going to work. Okay, let's try it. Let's see that it's not going to work. We don't know why it's not going to work. We'll see if you catch it. Okay, so I'm going to call language 3 with example 3. Okay, and I get undefined variable x. Okay, go back over here. In this expression, x is undefined. But why is that? It's right there. Anybody, this is you have to really think hard. What went wrong here? Why is x undefined when it's right there? You have to think back how we defined functions all along. Has to do with the evaluator. We go to apply function. We're calling a function. Here's evaluate apply. So remember something about evaluate apply that would explain this riddle. When we apply f and we try to execute this expression, see, we look at maybe call up the abstract syntax tree. You're calling f with parameter 10. Here's the lambda expression. Z is 10. X, Y, and Z. Well, you expect X to be right there inside the begin, and you expect Y to be right there inside the begin. But what's true about our lambda expressions? So I remember how they work over here. Where do the lambda expressions look for their variables? The key is this line right here.
And they look in their subtree for them.
Well, what do you mean their subtree?
So if it's not below where it says lambda, then it won't.
They don't look in this tree. No, first of all, they do not find variables in the abstract syntax tree. They don't find variables in the abstract syntax tree. Where do they find variables?
The environment.
Yeah, the environment. Okay, so you remember it's not shown in this picture, but at runtime,
new environment. So
pardon?
sorry, it creates a new environment.
Yes, yeah. And then what's that environment linked to? Now the environment would hold, in this case, Z linked to 10, right? But what's the environment linked to? We saw some pictures of it over here. See how a local environment was linked to the global environment? A local environment was linked to the global environment. But what's true about function activation environments? Same as the C language. When you call a function, where does it find its non-local references?
In the global.
In the global environment. You can see it right there. The functions are always linked to the global environment. So now notice that there's no X there.
Right.
So that's why I couldn't find X. See, the function is linked to the global environment. What we really needed to do was link it to this local environment. That's what we meant by dynamic scope. Okay. Now we can fix this by giving this language dynamic scope. Instead of linking to the global environment, we link to the current environment. Okay, so change that to this. Change it to dynamic scope. Okay, change this. Change it from global environment to ENV. So now we're using dynamic scope. Okay.
You accidentally typed C instead of V.
Oh, yeah. And I want the line above it to be commented out. There. Okay. Right. So I'm setting the local environment. I'm chaining it to the current environment now. So now I'm going to chain the activation record to this guy that's highlighted here. And then that guy will be connected to the global environment. So I'm going to go activation environment, local environment, global environment. And then my function can find its local variables. Okay. So I have to change from static scope to dynamic scope. Okay. And in the history of programming languages, this is why they ended up with dynamic scope, because they got this problem and they said, oh, we can fix this real easily. Okay, now we've made a change in the evaluator. To show that this works, we need to recompile the evaluator. So I'm going to go over here and I will clean everything, build all the classes, build the jar, build the jar file again. Okay, then clean up again. Okay, so now this is now this jar file is the interpreter with dynamic scope instead of static scope. Okay, so let me rerun that program. Okay, see, it didn't crash it again. Now let's check that it kind of did what we think it should do. Okay. Okay. I've got a program with a local environment. Oops. There's the local environment. The local environment creates a local variable X, a local variable Y, then there's a local function that references X and Y and its parameter. Then it calls the function right away. Okay, so there's the begin block, there's the local environment. The local environment has an X in it. Then the local environment's got an X and a Y in it. Then the local environment's got X, Y, and an F in it. Now here's the call. Now here's the call. See, the function activation environment is hanging off the local environment, which is hanging off the global environment. Okay, and the global environment doesn't have anything in it right now. I didn't put anything in the global environment. Now when I call this function and I evaluate the function, now it finds Z in the activation environment and it finds X and Y in the local environment. Okay, so I think it looks like I fixed things. Okay, but I haven't fixed things very deeply. There's still a more deep, now I'm going to write the code a little bit trickier and it'll still be broken. Okay, so I've gone from, I've changed the language to use dynamic scope, and it looked like I fixed the problem. And this is kind of what motivated dynamic scope a long time ago. But now I'm going to do another example. Okay, I'm going to do a more serious example. Okay, need for closure. Look at the code here. Okay. Now I'm going to do this thing. I'm going to try to make things escape. This is the real problem. I have not used the fact that these are first class functions yet. See, I haven't really mixed first class with nested functions yet. Okay, I did back here. Okay, but here I mixed first class with nested, but I did not make any non-local references. Here I made a non-local reference, but I didn't use the fact that these were first class functions. Okay, so here I used non-local references. Here I used first class functions. I didn't mix them yet. Now I'm going to mix them. And this is when everything blows up. This is historically when they found out that this is when they really realized that they had to think hard. They want to mix the idea of a non-local reference with the idea of a first class function. And that took a long time, some very smart people to solve this problem. Okay, so here's what I'm doing. Here's a global variable. I'm going to let my function escape into that global variable. Then I create my local environment. I have a local variable X, a local variable Y. My function refers to the local variables X and Y. Okay, and then my function G, then I let my function F escape to this function G. Okay, now I try to call G. Okay, now this is not being called in a local environment. So when you call G, you're going to link its activation record to the global environment. Okay, so then you'll call G, and G will be tied to this function here. This function will make reference to this X and Y, but that local environment was deleted when you got to this line of code here. So now you've got G referencing variables that no longer exist. Okay, you have G referencing variables that no longer exist because this environment has been at line 11. This environment is gone, so it's deleted. Okay, but then we call G. G is still storing the reference to F. So it's just pointing to that lambda expression. That's not a big deal. You create an activation record for F, and then F, it won't be able to find X and Y because there won't be any X and Ys for it to look at because this environment no longer exists. So there is no environment. Now we're back to just G pointing to the global environment, and there is no environment for X and Y. Okay, so let's let this run and watch what happens. Okay, now I'm not changing the language here. This is just the example. So I'm still running language 7E with dynamic scoping. Okay, so language E with dynamic scoping, and there's the example. Okay, see, I'm back to undefined variable X. Okay, so let's trace through what happened. Okay, let me clear the screen so we can know what, okay, so there's where our function starts. Okay, here's what it looks like. there's a global variable, there's a nested block. Within the nested block, we create a local variable x, a local variable y, and a local function f. Okay, then we set g to f. Now that's not really so much of a problem. G just points at this lambda expression, which is part of the abstract syntax tree. So G's not really got any problem. But when we call G, we're outside of, we're at the top level now. So G gets called with its activation record tied to the global environment. Then when you try to run F, you get a reference to an X, and there is no X left. The environment that X was in has been deleted. So let's follow it down as we go along here. Here's the global environment with G in it. G's just got this dummy variable Z, 0. Here's the global environment with the local environment tacked on, and it first gets an X. Then here's the global environment with the local environment with X and Y. So the global environment with the local environments with X and Y. So we've done var X, var Y. Now the next one is going to put this F in the local environment. So that's this line here. Now we have a global environment with a local environment with X, Y, and F. Then we execute this set G to F. So that would be this here. Notice that G now points at that lambda expression. Okay, so X, Y, and F are in the local environment, and G is a pointer down here into this lambda expression. No problem so far. Okay, now we get to this line here, and the local environment disappears. Okay, so that's here, and there's no more local environment. See, this local environment gets thrown away at this point. So it doesn't exist anymore. But G is still got that lambda expression in it. See, G still got that lambda expression with the X and Y's in them. Then you create the activation record to call G. Okay. The activation record to call G has got its parameter Z bound to 100. But then when you go look for X, it's nowhere to be found. The activation record that held X has been deleted by now. Okay. All right. So this is harder to solve. This problem, what we've done is we've combined the first classness of a function in that it can be assigned to a variable with the nestedness of the function because it came inside of something with local variables. We've combined first class with nested, and now it's not so obvious. How do I stop? Here's the question. How do I keep this guy from being deleted? And how do I make this guy refer to the thing that we could kept from being deleted? Okay, so I've got two problems. I need to preserve this environment. So even though I get to this point here, somehow I have to preserve that environment. And I have to make G refer to the reserved environment. That's what closures are. Closures are a way of saving environments for later use. Okay, so now there's no way to go and fix language 7 and do this. I mean, the fix is to make it in language 8. Okay, at this point we've hit the limit of what we can do with language 7. We can't somehow fix language 7 can deal with first class functions as long as they're not nested. And it can deal with nested functions as long as they're not first class. But language 7 won't work if you combine the two because of this example here. When you combine the two, when a nested function with non-local references escapes out of its local environment, it loses access to its local variables. Okay, so when a local function, a nested function that makes non-local references, when it escapes outside of that local environment, then it loses access to its local variables, and it's got a problem. Okay, if the nested function doesn't escape, it can make non-local references. If the nested function escapes, that's okay if it doesn't make non-local references. And there were languages in the history of programming languages that had all these rules. They had all kinds of rules, like if you had a nested function and it made non-local references, then it couldn't escape. But if a nested function didn't make non-local references, then it could escape, because the languages they couldn't combine these. So if you look at languages like Pascal and maybe Ada, so the languages in the 70s, they stumbled around with these ideas. So they would have special cases like, oh, you can have a nested function, but your nested function can't make non-local references, and then you can return it. Or you can have a nested function that makes non-local references, sure, but then you can't return it. Okay, so you would have various. They tripped all over themselves to try to sort this out. The C language looked at all that and said, phooey. The C language said no nested functions. Okay, the C language just said, yeah, this is a mess. They didn't want to. They knew how to solve the problem, but they didn't want to, so they just avoided the problem. The C language has no nested functions. If there's no nested functions, then you don't have to worry about nested functions escaping, and you don't have to worry about nested functions making non-local references to local variables. If you eliminate nested functions, you get rid of all these problems. Okay, so the C language made the choice of no nested functions, and Java kind of followed suit, kind of. Okay, but I'm not sure why they must. I think they made the right decision for the time. Languages like Pascal and Ada and some other ones at that time, they tried to split the difference, and they tried to kind of like allow some kinds of nested functions but not allow other kinds of nested functions, and to allow some kinds of non-local references but not allow other kinds of non-local references. I think they ended up with just too much complication. Yeah, they just ended up with things that were too complicated. So the C language kept it simple and just said no nested functions. That's language 7. Our language 7. No nested functions. Okay. All right. Now, solving this problem here of trying to have you both things, nested first-class functions, requires closure. It requires you to come up with a scheme so that this local environment can somehow be preserved. Well, actually, so it would be this local environment needs to be preserved so that when I call this function G, it has access to that local environment. Even though the local environment disappears here. See, the local environment by definition disappears, the local environment goes out of scope. But what we want to do is we want to have a way of preserving it. Okay. So that brings up the notion of a closure, a device that will allow this local environment to survive that line 10. That local environment will survive line 10. Well, let's see that. Let's take this code and copy it to language 8. So let's take this need for closure. Let's put it in the language 8 folder and see that it'll work now. Okay, let me open a command window here, and I'll run it, and we'll watch what happens here. Everything's a lot trickier here. Closures have a reputation of being an advanced topic in computer science. JavaScript has closures, and it drives 99% of JavaScript programmers don't understand closures. Okay, and the only ones who understand closures are the ones who've actually really studied computer science well. But JavaScript makes use of closures a lot. So you find just gazillions of web pages on the internet trying to explain closures to your average JavaScript programmer. It's considered a pretty advanced topic. So let's watch language 7 deal with this. Or language 8 deal with this. So here's the language 8 interpreter, and this is our need for closure example. Okay. Now it ran fine. It ran to completion. Okay. Let's trace through and kind of see if we can see what it did differently. Okay. This is going to work now. G Now, let's see, what should the result of G be? It's 100 plus X plus Y. So the answer should be 115. So the result should be 115. See, there's our right answer. So it worked fine. Okay, so go through the steps. Most of it looks the same. There's the global environment with the G dummy variable. There's the global environment with the local environment hanging off of it. The local environment declares X, then the local environment adds Y, then the local environment adds F. Okay. Notice there's something interesting here. The value of F is no longer the lambda expression. The value of F is this thing called a closure. That value there is the tricky thing. If we, I don't know if I still have it open. See, if you look in here, the value of L was the actual lambda expression. That's a naive thing to do, that the value of a function is the code of the function. That's what C wants to do. The value of a function is a pointer to the address of the function. The value of a function is a pointer to the address of the function. That's exactly what C does. Keep it simple. Notice over here, that's not what it is. The value of function, this stands for IPEP pair. That's instruction pointer, environment pointer. Here, this is just an instruction pointer. It's pointing at the code. So it's an IP. It's an instruction pointer. That's what a function name is in C. It's a pointer to the code that executes the function. A closure is an instruction pointer combined with an environment pointer. So it's called an IPEP pair. That's an old-fashioned name for closure. I think it's a great name for closure, because I think one of the big problems with closures being confusing is because nobody can figure out what closure means. Yeah, and this is more descriptive. If you look in any advanced programming book, they'll tell you that a closure is an instruction pointer and an environment pointer. And if you look at older books, they actually call them IPEP pairs. And I like to keep that old habit. When I first learned about them, I learned of them as IPEP pairs. And I still think that's a great name for them. It's an instruction pointer, which is what a C function value is, combined with a pointer to the environment that needs to be preserved. And the key is that if you combine two pointers together in a strut, that extra pointer prevents the environment from being garbage collected. So that's the thing that makes the environment hang around for us. Well, we'll do this in more detail, but that's the trick. By having a pointer to the environment doesn't get garbage collected. Okay, so a closure is an IPEP pair. And then this is just the address of the closure in memory. Okay, that's just Java's way of that. I didn't put a toString method into the closure, so it's an IPEP object at that address. Okay, so the local environment has got the X, the Y, and the F in it. Okay, then let's see. There's one of those repetitions. I'm not sure what. Let's see. What was that repetition for? Oh, that's when G. I'm sorry. That's when G is set to be equal to this. See, now we pass this value to G. See, that's what G is. G is now a closure. So the F, which was, if we line these up, the wrong version and the right version, the wrong version copied that code pointer into G. See, that code pointer was copied into G. G just points at the code, exactly like C does. It copies the pointer to the pointer. So the code pointer, the instruction pointer here, gets copied to the instruction pointer here. Now the pointer to the IPEP pair is passed to here. So now the pointer to the IPEP pair is passed to G. So G points at both the code and the environment, both. And the environment pointer is this box here. It's pointing at this box. Okay, so the IP points at that lambda expression. The EP points at this box, the environment. So G is pointing at that environment. So that environment doesn't get deleted. Okay, all right. Now you call the IPEP pair. See, this is the last function. This is the last thing we do. We call this is the equivalent of this one down here. When we called F down here, when we called G down here, G was pointing at a lambda expression with undefined variables in it. Over here, when we call G, we call the function. Okay. When we call the function, we get that environment back again, because the EP and the IPEP pair, the EP preserved this pointer here. So now this function's got that local environment restored. That local environment actually, I should have put a step in between here so that you could see that that local environment actually disappears, but then the EP restores it for us. Okay. I should have put up here something in between that line of code and that line of code so that you could kind of see that the local environment actually goes away. Like I could have put a line of code in here, just created a dummy variable, and you could see that the local environment goes away. Okay. But then it gets recreated when we call the closure. When we call the closure, we get the local environment back, and the function now F can find its X and its Y. Okay. Z is 100. X is 5, X is 10, and G, and then the function G, we get the value of the lambda from G, and we call the function Z with X and Y, and it get the right result, 115. Okay, all right. The takeaway is that nested functions are okay as long as they don't escape, or as long as they don't make non-local references, or, well, nested functions that don't make local references are allowed to escape. Nested functions that do make local references are okay as long as they don't get allowed to escape. Okay, so nested functions that make non-local references are okay if they can't escape. Nested functions that escape are okay if they don't make non-local references. Or if they do make non-local references, you can't let them escape. Notice it's a real confusing. I'm saying it real fast, but it's the combination of nesting and non-local references that cause a problem. Nesting non-local references and escaping, making them first class. Okay, that's what this example here does. Okay, non-local references that are assigned to a variable and the variable escapes the environment that it's defined in. So we have non-local references, first class functions that escape. That combination is the thing that took years to sort out. If you have non-local references to nested functions that are allowed to escape, what do you do? Okay, and the solution was this guy this was solved in the 70s in the Scheme programming language. They were the ones, as far as I know, they were the first ones to solve this problem. The Scheme programming language in the 70s, and it was Guy Steele who did this. This guy here, he's the one, real famous guy. He's the one, and he was a grad student when he did this. He wasn't even a professor. He did this. This was his thesis. His PhD thesis was solving this problem. So he did this as a graduate student. He solved this problem of what do you do? How do you make sense of combining essentially this, making this run? It's 10 lines of code. Yeah, and he got a PhD out of figuring out how to make this 10 lines of code run. Now we know what the solution is. Now we can teach it even in undergraduate classes. This is taught even in undergraduate classes in some schools. Now we can teach how to make that 10 lines of code work. Now, to make that 10 lines of code work, you need to make more, you need to go back over here. You don't actually need to make a lot of changes to the evaluator. You probably add another 20 or 30 lines of code to the evaluator. It's not a lot of code to make it work, but it's code that requires a lot of thought. So he figured out what to do to make this work, and he created the Scheme programming language to make that, to do it. The Scheme programming language was the proof of concept that his ideas worked. Okay. And then the scheme programming language became one of the most famous languages around because it made such big jumps forward in designing programming languages. Okay, so we're trying to solve the problem. Okay, we ran out of time, we'll quit, but we're solving the problem of first class functions that make non-local references that escape. Escaping first class functions with non-local references. Remember, non-local references are fine if you don't escape. Escaping is fine if you don't make non-local references. Okay, that's language 7 still. Okay, well, but language 7 needed dynamic scope to solve. This worked fine in language 7. If you did this, you need a dynamic scope. Okay, so to make this work, you still need a dynamic scope. And that's how Lisp ended up with dynamic scope, because it was able to make this work. Okay, but this one's trickier. Okay, this is the one that becomes really tricky. How do you make nested functions that make non-local references that escape from their local environment? How do you make those work? Okay, and that's where the hard part of closures comes in. And then once languages have closures, it turns out you can write all kinds of elegant code using a closure. It wasn't just this is all clever little hack. It turned out that this provided very elegant programming models. So languages were able to do all kinds of clever things that they couldn't do before once they had this notion of escaping non-local references in first-class functions. It provides for some very elegant, and that's the whole basis of modern Java, modern C++, Haskell, ML, all of the modern languages now, they're based on this idea of closure. JavaScript, a lot of the tricks in JavaScript programming are based on making use of these closures. Okay, all right. So we'll quit there, and we'll keep hammering away at this. Like on Wednesday, we'll go back through these again, and we'll see how language 8 implements closures. So right now we're trying to motivate what's needed, and then we'll see how to solve the problem. What do you actually do in language 8 to solve the problem? Okay. And one last thing. Let's see, what is it? You have a programming assignment due today. So if anybody got questions about it, please send me email, and I'll have another program assignment up there by Wednesday. Hopefully by Wednesday, your next one will be up there too. Okay, and it'll still be language 7. It's actually not going to be a homework assignment about language 8 yet. There'll be another program assignment about language 7. Okay, so it won't make use of the stuff we're talking about. So even the next program assignment, it'll still be based on very much on language 7. Okay, anybody got any last second question? Any question? Okay, look at these examples and think about them. Try to remind yourself what was good and what was bad. What did we mean by going from here to here to here to here? Try to remember, what was the progression from here to here to here? What is it we're trying to build up? What is it we're trying to demonstrate? Okay. And then we'll look at examples using JavaScript. Okay, we'll use JavaScript as a language, for example, so you get a sense of how people are really using this in the real world. Okay, all right. So I'll quit there, and on Wednesday we'll start looking at the implementation of language 8. Okay, so see you on Wednesday. Bye.